In this video, I will be discussing about another geometrical application of differential equations. And the second geometrical application of differential equation is the isogonal and orthogonal trajectories. So what are isogonal and orthogonal trajectories? A one-parameter family of curves g of x, y, and z, which is equal to 0, is called an isogonal trajectories if this family of curves g intersects every curve at a given family of curves r of x, y, and z, which is equal to 0, at a fixed angle theta. So first and foremost, there must be a family of curves. And in this family of curves, another family of curves that intersects every curve of the given family of curves at a fixed angle theta. And the angle formed between these two lines or curves of each family is given by this very familiar formula from our analytic geometry, which is the angle formed by the two intersecting lines, which is equal to the slope of the second line minus the slope of the first line divided by 1 plus the product of the slopes of the first and the second line. Now, these are lines because to find the angle formed between two curves is to find the angle formed by two tangent lines at the point of tangency, where this first slope is the derivative of y with respect to x for the given family of curve r, and this second slope is the first derivative of y with respect to x of our isogonal trajectories to the given family of curves r. And what is an orthogonal trajectories? A one-parameter family of curves, say h of x, y, and z, which is equal to 0, is called an orthogonal trajectories if this family of curves h intersects every curve at given family of curves r, which is a function of x, y, and z, which is equal to 0 at right angles. So these orthogonal trajectories is a special kind of isogonal trajectories because the angle formed by the two intersecting curves from each family is at a right angle, and the relationship between the slopes of two intersecting lines or curves from each family is given by this equation that their slopes are negative reciprocals to each other. And to illustrate the application of the isogonal and orthogonal trajectories, we'll illustrate that one in problems. So find the isogonal trajectories intersecting at an angle of 45 degrees to the family of hyperbolas given by this equation x squared minus y squared, which is equal to c. Now, to solve this equation, we are given that the equation of the family of curves r of x, y, and z, which is equal to 0, is given by the equation x squared minus y squared, which is equal to c. And the slope of this family of curves r is the derivative implicitly of this equation. So the derivative of x squared implicitly is 2x, and the derivative of y squared is 2y dy dx, because we are taking the derivative with respect to x, and the derivative of a constant is 0. So moving this term to the right hand side of this equation, we have 2x, which is equal to 2y dy dx. And dividing both sides of the equation by 2y, we have 2x divided by 2y, which is equal to the derivative of y with respect to x. Then therefore, our derivative of y with respect to x is equal to x over y. So this is the slope of our given family of curves r. So this is now our first slope function for the given family of curves r. And the slope of the family of curves g is the derivative of y with respect to x for this family, with an angle between them of 45 degrees. So substituting these two slopes to the formula, we have tangent theta is equal to the derivative of y with respect to x of our unknown family of curves minus the derivative of y with respect to x for our given family of curves divided by 1 plus the product of these two slopes of the two families of curves. And we know that our angle theta is 45, so we have tangent 45 degrees is equal to the derivative of y with respect to x for our unknown family of curves minus the slope of the given family of curves, which is x over y. And this is divided by 1 plus the derivative of y with respect to x for the unknown family of curves times the slope of the given family of curves r. Then we know that tangent 45 is 1, so this is 1, which is equal to the derivative of y with respect to x minus x over y divided by 1 plus x over y times the derivative of y with respect to x. And if we multiply both sides of the equation by this denominator here, we have 1 plus x over y times the derivative of y with respect to x, which is equal to the derivative of y with respect to x minus x over y. And if we look for the LCD between the two, we have y dx, and the numerator is y dx plus x dy. And also, if we find the LCD between these two terms here, we have also y dx. So the numerator is y dy, and this one becomes x dx. So multiplying both sides of the equation by y dx, these two y dx's here will be cancelled. So what remains is y dx plus x dy, and this is equal to y dy minus x dx. And we noticed that this is already an integrable combination because this is the derivative of a product of x and y. And this differential is equal to y dy minus this x dx. And integrating each term in this equation, we have xy, which is equal to y squared over 2 minus x squared over 2 plus the constant of integration c prime. So multiplying both sides of the equation by 2 so that we can eliminate these 2 in the denominators, we have 2xy, which is equal to y squared minus x squared plus 2c prime. And moving these two terms to the left-hand side of the equation, we have x squared plus 2xy minus y squared is equal to the constant c, because this 2c prime is just a constant. So c is just 2c prime. And this is our answer for this problem, where this equation represents a family of curves wherein each curve intersects the given family of curves at an angle of 45 degrees. So let's proceed to our example number 2. Determine the isogonal trajectories of the family of curves x squared plus y squared equals c if the tangent of the angle between them is negative 1/3. So in this problem, we are given the equation of the family of curves. So this is our r of x, y, c, which is equal to 0, is given by the equation x squared plus y squared equals c. And to solve for the slope of this family of curves, we need to find the derivative of this equation implicitly. So this is 2x plus 2y dy dx, which is equal to 0, because the derivative of a constant is 0. So moving this term to the right-hand side of this equation, we have 2y dy dx, which is equal to negative 2x. And dividing both sides of the equation by 2y, we have dy dx, which is equal to negative 2x over 2y. Then therefore, our derivative of y with respect to x for this family of curves r is negative x over y. So this is now our first slope, the slope function of the given family of curves. And the slope of the unknown family of curves is also the derivative of y with respect to x for this family of curves, with tangent of the angle between them, which is negative 1/3. So substituting these two slopes, we have this tangent theta, which is equal to the slope of the unknown family of curves minus the slope of the given family of curves divided by 1 plus the product of these two slopes, the slope of the unknown family of curves and the slope of the given family of curves. And it is given that the tangent angle between them is negative 1/3. So this is negative 1/3, which is equal to the derivative of y with respect to x minus the derivative of y with respect to x, which is the slope of the given family of curves. So this is minus the negative x over y, and this is divided by 1 plus the derivative of y with respect to x times negative x over y. And simplifying this equation, we have 1 over the negative 3, which is equal to the derivative of y with respect to x plus x over y. And this is divided by 1 minus x dy over y dx. And multiplying both sides of the equation by the product of these denominators here, we have 1 times 1 minus x dy over y dx. And this is equal to negative 3 times dy dx plus x over y. So we have 1 minus x dy over y dx, which is equal to negative 3 dy dx minus 3x over y. And grouping all the terms having dy at the right hand side of the equation, we have 1 plus 3x over y, which is equal to x dy over y dx minus 3 dy over dx. And combining these two fractions here, we have y plus 3x over y, and this is equal to these two terms here. And if you're going to factor out dy dx between the two, we have x over y minus 3 times dy dx. And combining also these two terms here, we have y plus 3x over y, which is equal to x minus 3y over y dy dx. Then solving for dy dx, this is y plus 3x over y divided by x minus 3y over y, which is the value of dy dx here. So therefore, our derivative of y with respect to x, which is the slope of the unknown orthogonal trajectories, is y plus 3x over x minus 3y. And multiplying both sides of the equation by the product of their denominators, we have x minus 3y times dy, which is equal to y plus 3x times dx. And then moving this term to the right hand side of the equation, we have y plus 3x times dx minus the quantity of x minus 3y dy. And you notice that this is not a separable differential equation because we have a sum of y and 3x here and the difference of x and 3y. But this is a homogeneous differential equation because the exponent of each term are equal. So we'll represent our y as vx. So our differential of y is v dx plus x dv. And substituting these representations to this differential equation, we have our y, which is vx plus 3x times the dx minus x minus 3y, but our y is vx times dy, which is v dx plus x dv. So distributing this dx to these two terms, we have vx dx plus 3x dx. And we'll distribute this negative to this binomial here. So this becomes plus 3vx. So this becomes positive and this x becomes negative times v dx plus x dv here. So multiplying these two binomials here, we have vx dx plus 3x dx plus 3vx times v dx is 3v squared x dx. And multiplying 3vx by this one here, we have plus 3v x squared dv. And multiplying this negative x to this v dx, we have negative vx dx. And this negative x times x dv, we have negative x squared dv here. And we know that this term and this term cancels each other. So we have these two terms as 3x plus 3v squared x times dx. And also this term, we have plus 3v x squared minus x squared times dv. And we can factor out the common monomial factor here, which is 3x. We have 1 plus v squared. And also this one, the common factor is x squared. So we have 3v minus 1 dv. And dividing both sides of the equation by the product of x squared and 1 plus v squared, we have 3x times 1 plus v squared dx plus x squared times 3v minus 1 dv divided by the product of this x squared and 1 plus v squared, which is equal to 0 because 0 divided by this one is 0. So this 1 plus b squared cancels. Then what remains is 3x dx over x squared. And this is added to 3v minus 1 over 1 plus v squared because these x squareds cancels each other. So this is equated to 0. But we can separate these two terms here. We have 3x dx over x squared plus 3v dv over 1 plus v squared, and then subtracted by dv over 1 plus v squared, which is equal to 0. And simplifying this term here, we have 3 dx over x, and this is added to 3 times v dv over 1 plus v squared minus dv over 1 plus v squared, which is equal to 0. And finding the antiderivative to each term of this equation, we have the integral of this one plus 3 times the integral of this one minus the integral of this one, which is equal to the integral of 0. But we can factor out this 3 here, so this is 3 times the integral of dx over x plus 3 times the integral of v dv over 1 plus v squared. But if we let this denominator as our u du must be 2v dv. So we need to add here a factor of 2. But to balance, we need to multiply here outside the integral symbol by 1/2. So that 1/2 times 2 is just 1, as if we have done nothing to this term. So this is also the integral of dv over the sum of 2 squares, because 1 is just 1 squared. And this is equal to the integral of 0. Then we know that the integral of dx over x is ln x, and the integral of 2v dv over 1 plus v squared is the natural log of 1 plus v squared. And then this is subtracted by the integral of this, which is the arctangent of v. So substituting back our original variable for this v, we have here our v, which is equal to y over x if you solve for v here. So we have 3 times the natural log of x plus 3 halves of the natural log of 1 plus y squared over x squared minus the arctangent of y over x. Then therefore, our final answer is 3 times the natural log of x plus 3 halves of the natural log of x squared plus y squared over x squared minus the arctangent of y over x, which is equal to the constant of integration c. And this is our final answer for this problem. And this is our equation of the isogonal trajectories, wherein each curve of this family of curves intersects each curve of the family of curves, which is x squared plus y squared equals c, at an angle whose tangent is negative 1/3. So let's proceed to our example number 3. Find the orthogonal trajectories to the family of parabolas y equals ax squared. Now, you see here in the drawing that we have a family of parabolas. Some are opening upward and some are opening downward. But you see here that parabolas are having vertices at the point of origin. But because we have here the constant a, it has different distances from their foci. So, since the given family of parabolas is y equals ax squared, then the slope of the given family is the derivative of this equation implicitly. So we have the derivative of y with respect to x, which is equal to a times the derivative of x squared, which is 2x. So we have now the differential equation, which is the derivative of the given family. So this is the slope of the given family R, and eliminating the arbitrary constant a, we just substitute the a value from the given equation y equals ax squared. So we have the derivative of our y with respect to x, which is equal to a, but our a must be taken from this given family, which is y over x squared. This is multiplied by 2x, since a is just equal to y over x squared from this equation. Now, simplifying this equation, we have the derivative of y with respect to x is equal to 2y over x, because we cancel one of the x in this x squared to this x in the numerator. Now, in this problem, we are looking also the orthogonal trajectories of this given family of parabolas, which we call this one as the family H. And the slope of this family H will represent this one as the derivative of the given family with respect to x with the angle of 90 degrees for every intersection of each curve to the given family, because this is an orthogonal trajectories. Then, substituting these two slopes, one for the slope of the given family of parabolas, and the other slope is the slope for the unknown orthogonal trajectories, we can use the relationship that the slope of the orthogonal trajectories is a negative reciprocal to the slope of the given family of parabolas. So, substituting the slope of the unknown orthogonal trajectories, which is this one here, we have the derivative of y with respect to x is equal to the negative reciprocal of the slope of the given family of parabolas, which is 2y over x. So, our derivative of y with respect to x is equal to negative x over 2y if we get the reciprocal of this one. Thus, we can simplify this equation by multiplying both sides of the equation by the LCD of these two denominators. So we have 2y times dy, and at the right hand side we have negative x times dx. And moving this term to the left side of the equation, we have x dx plus 2y dy, which is equal to 0. And integrating each term in this equation, we have the integral of x dx plus the integral of 2y dy, which is equal to the integral of 0 here. Now we know that the integral of x is x squared over 2, and the integral of 2y is 2 times y squared over 2, and the integral of 0 is some constant c prime. And multiplying both sides of the equation by 2 so that we can eliminate this 2 in this denominator, we have x squared plus 2y squared, which is equal to 2c prime. And we know that 2c prime is just a constant, so we can write this answer as x squared plus 2y squared, which is equal to the constant c. And this is our answer for this given problem, that the orthogonal trajectories of the family of parabolas, which are this one here, are ellipses, because this is an equation of the family of ellipses. So if you draw here an ellipse, so we have family of ellipses here, and these are ellipses whose center is at the point of origin. You see that every ellipse intersects every parabola at an angle of 90 degrees. So you see here, these are 90 degrees. So every curve, every ellipse is intersecting every parabola at an angle of 90 degrees here. And that is what we mean by orthogonal trajectories. Now, let's proceed to our last example here. Determine the orthogonal trajectories of the family of circles whose equation is x squared plus y minus r quantity squared is equal to r squared. And also find the particular trajectory which passes through a specific point whose coordinates are 5 and 5. Now, the given family, which is a one parameter family, is x squared plus y minus r quantity squared, which is equal to r squared. We can simplify this one to solve for our r. So we have x squared plus y squared minus 2ry plus r squared, which is equal to r squared. Now you can subtract both sides of the equation by r squared, so what remains is x squared plus y squared minus 2ry, which is equal to 0. And isolating this term, because this contains r, we have x squared plus y squared is equal to 2ry. And then dividing both sides of the equation by 2y, we have x squared plus y squared over 2y, and the fraction is just equal to r. So we are now isolating the r because we want to eliminate this constant r. And to eliminate this constant r, we take the derivative. And the derivative is the slope of the equation. So the slope of this given family of circles is the application of the quotient rule. So we have the square of 2y, which is the denominator, and we multiply 2y in the denominator by the derivative of the numerator, which is 2x plus 2y times the derivative of y, which is dy dx. And this will be subtracted by this numerator, x squared plus y squared times the derivative of the denominator, which is 2 times dy dx. So this is the implicit derivative of this fraction here. So multiplying both sides of the equation by this 2y quantity squared, we have this numerator as 4xy plus 4y squared times the derivative of y with respect to x minus the quantity of 2x squared times the derivative of y with respect to x. If we are going to distribute this factor here to this binomial, and we still have minus 2y squared times the derivative of y with respect to x, and the whole thing is equal to 0. Now, combining this term and this term, because they are like terms, we have 4xy plus 2y squared times the derivative of y with respect to x minus 2x squared times the derivative of y with respect to x. Because if you subtract 4 by this one, we have 2. And dividing both sides of the equation by 2, because we have a common of 2 here, we have 2xy plus y squared dy dx minus x squared times the derivative of y with respect to x, which is equal to 0. And moving these two terms to the right hand side of the equation, we have 2xy, which is equal to x squared times dy dx minus y squared times dy dx here. And factoring the common factor for these two terms, we have x squared minus y squared times the common factor of dy dx and dividing both sides of the equation by this factor here, x squared minus y squared, we have 2xy divided by x squared minus y squared, which is the value of our dy dx, which is now the slope of the given family of circles. And also, we can represent the slope of the unknown orthogonal trajectories, which we represent this one as h is the derivative of y with respect to x for this unknown family of curves with an angle for each intersection of 90 degrees, because this is an orthogonal trajectories. So, substituting these two slopes, the slope of the unknown family of curves and the slope of the given family of curves, we can use the relationship that the slope of the unknown family of curves is equal to the negative reciprocal of the slope of the given family of curves. So we have the derivative of y with respect to x, because this is the representation of the slope of the unknown orthogonal trajectories is equal to negative 1 over the slope of the given family of circles, which is 2xy divided by x squared minus y squared. And multiplying the numerator by the reciprocal of the denominator, we have the derivative of y with respect to x is equal to the negative 1 times the reciprocal of the denominator, which is x squared minus y squared over 2xy. And the negative of the numerator is just y squared minus x squared, and this is divided by 2xy. And multiplying both sides of the equation by the LCD of these two denominators, we have 2xy dy, and at the right we have here y squared minus x squared quantity multiplied by dx. And distributing this dx to this binomial, we have 2xy dy, which is equal to y squared dx minus x squared dx here. And moving these two terms to the left hand side of the equation, we have 2xy dy minus y squared dx plus x squared dx, which is equal to 0. And dividing both sides of the equation by x squared, we have 2xy dy minus y squared dx divided by x squared, and this x squared here will be cancelled. Now you see that this one is already an integrable combination, because this is just the differential of the quotient of y squared over x. And you can check that the derivative of this quotient is this one here, that we square this denominator, and that is x squared, and then we multiply this x by the derivative of y squared, which is 2y dy, and subtracted by this y squared here times the derivative of the denominator, which is dx. Thus, we can find easily the integrals of these two terms. So we have the integral of the differential of y squared over x plus the integral of dx, which is equal to the integral of 0. And we know that the integral of the differential is just y squared over x, and the integral of dx is x, which is equal to the constant of integration c prime. So combining these two terms, we have y squared plus x squared all over x, and this is equal to c prime. So multiplying both sides of the equation by x, we have y squared plus x squared minus c prime x, which is equal to 0. But this c prime x, I can rewrite this as negative 2c prime x, so that I can complete the square for these terms that contains x's, because this 2c prime is just a constant. So it's okay that I will express that constant as 2c prime. And to complete the square, we have to get the half of the numerical coefficient for x, and the half of 2c prime is just c prime. So this is added to c prime quantity squared, and because we are adding c prime squared at the left, we need to add c prime squared at the right. And we can now write this one as a perfect square, which is x minus c prime quantity squared. And you can check that this square of this binomial is just this trinomial. So we have this equation now. Or we can write this one as y squared plus x minus the r quantity squared, which is equal to r squared, so that it looks like an equation of family of circles whose center is at the point r0, but with radius of r. So therefore we say that the orthogonal trajectories are also circles with center at the point r0 and with a radius of big R. So these are circles whose centers are on the x-axis with radius r. And for the particular trajectory which passes through the point 5, 5, we can substitute this 5, 5 to our x and y here. So we have y, which is 5, so 5 squared, plus x, which is 5, so 5 minus r quantity squared, which is equal to r squared. And we can simplify this one as 25 plus 25 minus 10r plus r squared, which is equal to r squared. And subtracting both sides of the equation by r squared, what remains is 50, which is equal to 10r. Therefore, our r is 5. Thus, our particular trajectory is having the r of 5. So we have y squared, which is added to x minus the r, which is 5, quantity squared, is equal to 5 squared, which is 25. Or you can write this one as x squared plus y squared minus 10x, which is equal to 0, because the positive 25 here and the 25 at the right cancels each other. Then therefore, the particular orthogonal trajectory is a circle whose center is at the point 5, 0 with radius 5. And this is now the particular trajectory that passes through the point 5, 5. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.